I'm going to begin by apologizing because I cannot draw. And I think that that's rather apparent from what you now see here as a typical titration setup that you'll see in the lab. So this right here is known as a burette. And down here we have an Erlenmeyer flask. Flask. And this is just a ring stand. So in other words, something to stand up both the flask as well as the burette that's up there. So here's what a titration is. Here's what a titration does. What we do is we start to fill this burette, and I'm going to give it a green color just because that keeps it different, up to almost the top. Usually the top. It doesn't have to be the top. Fine, if it's the top, then it's the top. And we put a certain amount of liquid down here in the flask. Now, what the difference is between these two guys? The information on this is unknown. So we have an unknown concentration of our stuff that's in the flask, most commonly. And in the burette, we have something that's known. So we know exactly what the concentration here is of the stuff that's filling the burette. So what we do with a titration is we take the stuff that we know what the concentration is and try to determine what the concentration is for our unknown, whatever that may be. This particular titration, I'm going to give as an example, is a titration between HCl and NaOH. Now, this is a typical acid-base titration and what you usually start with when you're doing a titration lab. And so here we have a strong acid that mixes with a strong base, and it gives you water and a salt, so it's rather innocuous. Well, in this case today, we're going to put the NaOH in the known category. So we have NaOH in our burette, and we're going to take HCl and put it in the unknown category. So that's what this guy has. It's HCl that is aqueous. In other words, you have it in water. And the NaOH up here is also aqueous, and it is in water. And before we start this reaction, and before we start most titrations, we put in there something that is an indicator. What I mean by an indicator is it's something that tells us when we finally have enough of whatever's in the burette that matches with what we have in the bottom to basically signify that we have the same amount of each of those together. So what we're going to use here is phenolphthalein. Now, I spelled that wrong because I always spell it wrong because, spelling and drawing are not my strong suits. But here's the point. What we have here is an indicator that tells us when we have more base than acid. Okay? So phenolphthalein goes from clear to like a pinkish color when we have more base than we have acid. So what we're trying to find when we do a titration is when this and this are equal. We call that the equivalence point. So that's the point in your titration in which they are the same. So you have the same amount of HCl as you have as NaOH. So the second you have a tiny bit more NaOH than you do HCl, your reaction vessel down here goes from clear to pink. And so that's why we add this phenolphthalein or indicator to tell us that we've gotten to the point that we want to get to. So you start with your burette rather full, and you mark down what the actual reading is up here. Honestly, it doesn't matter that you start at 0 because you're basically just trying to get it so that you've got a relatively full burette. And this little guy over here is called the stopcock. And when you open that stopcock, your green stuff from above will start to drip down into where you have your solution. And that means that this stuff up above starts to drain, and you can end up with, less and less and less of the stuff that you have up here. So as this goes away, you'll eventually hit a point that down below, this guy hits that equivalence point. Say he turns that pinkish or red or whatever it may be. The point at which this turns into pink, so this value is pink, what that means is that however much NaOH you added from above is equal to the amount of HCl you had down here below. In other words, in moles, you had the same amount of moles that you added from up top as to what you end up having in the HCl down below. And we can use those values mathematically. So you go and you say, okay, well, here's my final volume. And you recorded your initial volume. And we're now going to use how much of that NaOH you added to determine how much HCl you had in your original solution. Not the final solution, like not what it looks like right now. Remember, we're trying to figure out how much HCl was in that original solution, because you usually have like a small sample of that solution and a large amount of it that you want to use to do something else. So that's really what we're trying to figure out here. So we go back and look at what we collect in the lab, and you might see something like this. So let's say in your first trial, whatever that is, initially you start with a 0.12 milliliter solution of your NaOH. So this is the NaOH. And your final burette reading may be this guy. I didn't talk about this, but the numbers are backwards on burettes, and that's for a purpose, and that's the reason why is because when you subtract your final minus the initial, it's still a positive number. Don't worry about it. It's really not that relevant for the numbers that we're doing right now, but just letting you know about that. So here's what we do. We take the final reading, we subtract the initial reading, and that tells us how many milliliters it is that we added of our known stuff that's in the burette. So let's say that you're going along and doing this, and we're actually using a 0.150 molar NaOH solution. Let's say that that was the case. Well, in that case, what you can do is you can figure out how many moles of NaOH you added. You want to do this because that is what's the most relevant thing to trying to figure out how much HCl you had as well. So if we have 29.19 moles, I can convert that to liters. That's 0.02919 liter. So I take that value and realize the 0.150 molar is 0.150 moles per liter. So I multiply those values out, and 0.02919 times 0.15 gives me that I have 0.00438 moles of NaOH. So remember, from our balanced equation, we know that NaOH and HCl are 1-to-1 because NaOH plus HCl gives you H2O plus NaCl. So everything here is a 1-to-1 relationship, right? Which means that this number of moles of NaOH is the same as the number of moles of HCl. So another way to do that, 438 moles of NaOH, I can multiply that and say for every 1 mole of NaOH I get 1 mole of HCl. So that means that we have the same number of moles of HCl. So now, we haven't talked about anything about that unknown HCl solution. So let's say that that unknown HCl solution was 25 milliliters. Whatever volume that was, we can use this volume here along with the number of moles here to determine the molarity of the original HCl solution. So if that's how many milliliters we have, we can multiply. We have 1,000 milliliters per liter. And that means we have 0.0250 liters of HCl solution. So if we take our moles, 0.0438 moles of HCl, and divide that by 0.0250 liters, that gives us a molarity of 0.175 molar HCl. So what we've effectively done is we've determined what the concentration is for an unknown solution of HCl. And that's the point of doing a titration. Now, typically, what you do is you repeat this in triplicate, in other words, in 3 different trials, and then you average all these values together to get a more precise or more accurate reading of what that HCl actually is. So these are things to consider when you're completing a titration lab. Thank you very much.